Hello everyone. I am Po Yen Lai, from the Department of Computer Science and Information Engineering at National Donghua University. Today, I will present my research, Enhancing Geister AI with Strategic Sacrifice and Anti-Loop Mechanisms. First, let me introduce the game. Geister is a 6x6 board game. Each player starts with 4 red ghosts and 4 blue ghosts. These pieces can be freely placed in the designated red squares, as shown in the image on the right. Each turn, a player chooses one piece to move. A piece may move up, down, left, or right into an empty space. It may also move onto an opponent's piece and capture it. During the game, you can clearly see all of your own ghosts and the number of remaining red and blue ghosts. However, you cannot see the exact positions colors of your opponent's pieces. This hidden information is what makes Geister unique. Next, I will introduce the main ways to win the game. There are 3 victory modes. The first victory mode is escaping with blue ghosts. When a blue ghost reaches the escape point, which is the top left or top right corner from the player's perspective, it can leave the board on the next turn. The second victory mode is capturing all of the opponent's blue ghosts. In the image labeled, "No Blue Ghost," the inverted triangles represent the opponent's pieces. Captured ghosts are shown with fading colors. If you capture all of the opponent's blue ghosts, you win the game. The third victory mode occurs when the opponent captures all of your red ghosts. In the image labeled, "No Red Ghost," the upright triangles represent your own pieces. If the opponent captures all of your red ghosts, you also win the game. These 3 rules are designed to balance each other. Blindly attempting to escape may allow the opponent to capture all your blue ghosts. Likewise, aggressively capturing pieces may accidentally eliminate the opponent's last red ghost, which can create additional risks. Why focus on rule-based heuristics? Machine learning methods often achieve stronger performance. However, they are usually considered black box systems. It is difficult to analyze why a specific decision was made. On the other hand, traditional minimax search algorithms are often overly conservative. The goal of this research is to improve the NAIADI 2020 minimax search baseline model. This is done by introducing additional evaluation functions and hybrid strategies. In this way, we can improve performance while still maintaining interpretability. The objectives of this research are threefold. First, we aim to improve performance through a deeper understanding of the game rules. Second, we introduce strategic innovation through sacrifice mechanisms and anti-loop mechanisms. Finally, we compare these improvements with benchmark models in order to optimize win rates. The hybrid decision-making architecture proposed in this experiment follows a clear logical process. After receiving board information, the system first updates its red ghost reasoning. Next, it attempts to perform Kanzen search in order to find a winning path. If no winning path exists, the agent enters the policy selection phase. At this stage, it chooses between the original purple strategy and our proposed sacrifice strategy. The selection is based on probability P. Finally, a loop checking mechanism ensures that repeated actions can be replaced. Analysis of the baseline data revealed a major limitation. The original purple and Kanzen strategies relied too heavily on the survival of the blue ghost. The survival weight of the blue ghost was 1,000 times larger than the distance weight. As a result, red ghosts moved mainly according to distance weighting. Their behavior resembled mimicking the escape path of the blue ghost, rather than acting as bait. To address this issue, this research designed a new evaluation method for red ghosts. Instead of mimicking the blue ghost's escape route, red ghosts are encouraged to actively approach enemies, block enemy movement, and become easier to capture. To further support this idea, this experiment introduced a sacrifice strategy. In the early game, when multiple red ghosts remain, an additional evaluation formula is applied. Through bonuses for proximity to enemies and adjacency, a red ghost can gain up to 500 points. This value is exactly half of the survival value of a blue ghost. As a result, the AI is encouraged to actively sacrifice red ghosts in order to lure opponents into traps. In the late game, the strategy changes. This experiment uses bonus points at escape points and defensive positions. Blue ghosts are encouraged to move toward escape points and receive double their base score. Meanwhile, red ghosts are prioritized for defending key positions and blocking enemy advances. To break deadlocks, This experiment implemented an anti-loop mechanism. This mechanism only activates when the AI detects a loop, and the strategic advantage score is greater than or equal to 0. The advantage score considers the relative number of red and blue ghosts, defensive formations, and retreat progress. When the AI has the advantage, it replaces repetitive moves with alternative actions. It also prioritizes maintaining a formation that keeps one red ghost and one blue ghost at each defensive point. At the same time, blue ghosts are pushed toward escape points, while red ghosts block enemy movement. This experiment tested the sacrifice strategy with usage probabilities from 0% to 100%. It was also combined with the cycle replacement strategy when an advantage was achieved. The resulting win rates were then compared against benchmark opponents. The experimental results show that the highest win rate, 66.2%, was achieved when the sacrifice strategy and the original purple strategy were each used with a 50% probability. In other words, red ghosts performed best when they mimicked escape behavior half of the time and actively approached opponents the other half. Using the primary baseline, this experiment conducted 500 self-play games. The original baseline showed a very high draw rate, reaching 61.2%, as shown in the figure on the left. This experiment was inspired by this stalemate situation. Conservative strategies attempt to avoid defeat by repeatedly selecting safe decisions, which can result in endless cycles. To address this issue, this experiment increased the diversity of search results through different strategies, and supplemented them with a cycle-breaking mechanism. As a result, the system successfully reduced loop stalemates and improved the overall win rate. Next, this experiment compared the best experimental versions of Sacrifice and Nayati 2020 in terms of win and loss types. The results in the table show that escape remains the dominant winning pattern. After changing the strategy, the proportion of wins through no red ghost conditions increased. This indicates that adding red ghosts as an additional evaluation factor can improve certain winning patterns. Increased randomness also led to more diverse outcomes, and overall, it improved win rate performance. However, not all eliminated draws became victories. Because of the aggressive strategies, losses caused by accidentally capturing red ghosts also increased. There were even situations where all blue ghosts were captured while attempting to escape. The number of no red ghost losses also increased against different opponents, because probabilistic strategies are not always optimal. In summary, the method proposed in this experiment can effectively break stalemates and improve win rates. However, there are still strategic trade-offs. Although the no-red win rate was improved through active sacrifice strategies, the randomness of these tactics also increased no-red lose situations. Breaking stalemates through aggressive captures does not always produce better results. This remains an important direction for future improvement. That concludes my report. Thank you for listening.